Yes, the lighting system and service entrance should be bonded together to create a common ground reference point for all electrical systems. This bonding ensures that any lightning surge is safely diverted to the grounding system. All electronic equipment, including the phone, data hub, and fire alarm, should be grounded to the service entrance ground bus. This prevents ground loops and ensures that excess current is safely discharged. The fuses blowing away from the service entrance suggest that the surge current is not entering through the service conductors. It could be caused by current swell from another source, such as a neighbor's lightning strike. Similar problems have been reported in buildings with the following issues: firstly, inadequate lightning protection system or lack of proper grounding; secondly, ground loops or poor grounding connections; thirdly, surge suppressors with inadequate capacity; and fourthly, current swells from nearby lightning strikes. Possible solutions include: firstly, inspect and upgrade the lightning protection system to ensure it meets code requirements; secondly, bond all electrical systems to the service entrance ground bus; thirdly, install a surge protector with adequate capacity at the service entrance and subpanels; and fourthly, investigate potential sources of current swell in the area, such as large electrical loads or nearby construction. Additional considerations are: firstly, check the equipment grounding conductor or EG continuity throughout the building to ensure a proper path to the grounding electrode; secondly, verify that the number 8 solid copper ground wire from the computer network and other equipment is properly connected to the service entrance ground bus or another approved grounding electrode; and thirdly, conduct a surge analysis to determine the magnitude and frequency of surges entering the building and design a protection system accordingly. A comprehensive approach to mitigating lightning and surge-related damage involves ensuring proper bonding, grounding, and surge protection throughout the electrical system. This includes the lightning protection system, the service entrance, and all sensitive electronic equipment. The goal is to create a low impedance path for surge currents to safely dissipate into the ground, minimizing the risk of damage to equipment and ensuring the safety of occupants. Bonding is the process of connecting different metallic parts of the electrical system together to create a common ground reference. This includes bonding the lightning protection system to the service entrance, as well as bonding all metallic conduits, enclosures, and equipment grounding conductors. Proper bonding minimizes voltage differences between different parts of the system, which can prevent dangerous arcing and equipment damage during a lightning strike or surge event. Grounding is the process of connecting the electrical system to the earth, providing a path for fault currents and surge currents to flow safely to ground. The grounding electrode system typically consists of ground rods, ground plates, or underground metallic water pipes that are connected to the service entrance ground bus. Proper grounding ensures that the electrical system is at a stable potential relative to the earth, reducing the risk of electric shock and equipment damage. Surge protection devices, or SPDs, are designed to protect sensitive electronic equipment from voltage surges and spikes. These devices are typically installed at the service entrance, subpanels, and individual equipment locations. SPD work by diverting excess voltage to ground, preventing it from reaching the protected equipment. It is important to select SPD with adequate surge current capacity and voltage protection levels to effectively protect the equipment from the expected surge environment. In addition to these basic principles, there are several other factors to consider when designing and implementing a lightning and surge protection system. These include the type of building construction, the location of the building, the sensitivity of the equipment being protected, and the expected frequency and magnitude of surge events. A thorough surge analysis can help to identify potential sources of surges and determine the appropriate level of protection required. When inspecting and upgrading a lightning protection system, it is important to ensure that it meets all applicable codes and standards, such as National Fire Protection Association, or FPA 780, standard for the installation of lightning protection systems. This standard provides detailed requirements for the design, installation, and maintenance of lightning protection systems, including grounding, bonding, and surge protection. It is also important to ensure that the lightning protection system is properly maintained and inspected regularly to ensure that it is functioning correctly. Proper grounding is essential for the safety and reliability of electrical systems. In addition to the service entrance ground, it is important to ensure that all equipment grounding conductors, or EGs, are properly connected and sized according to the National Electrical Code, or NEC. The EGC provides a low impedance path for fault currents to flow back to the source, allowing overcurrent protection devices, such as circuit breakers and fuses, to quickly trip and de-energize the circuit. Ground loops can occur when there are multiple ground paths between different pieces of equipment. This can create circulating currents that can cause noise, interference, and equipment damage. To prevent ground loops, it is important to ensure that all equipment is grounded to a common ground point, such as the service entrance ground bus. Surge suppressors with inadequate capacity can be a major cause of equipment damage during surge events. It is important to select surge suppressors with adequate surge current capacity and voltage protection levels to effectively protect the equipment from the expected surge environment. The surge current capacity is the maximum amount of current that the surge suppressor can safely divert to ground. The voltage protection level is the maximum voltage that the surge suppressor will allow to pass through to the protected equipment. Current swells can be caused by a variety of factors, including lightning strikes, utility switching operations, and large electrical loads. These swells can cause voltage fluctuations and current surges that can damage sensitive electronic equipment. To mitigate the effects of current swells, it is important to install surge suppressors at the service entrance and subpanels. It is also important to ensure that the electrical system is properly grounded and bonded to provide a low impedance path for surge currents to flow to ground. When investigating potential sources of current swell in the area, it is important to consider factors such as large electrical loads and nearby construction. Large electrical loads, such as industrial equipment and data centers, can draw large amounts of current from the utility grid, causing voltage fluctuations and current surges. Nearby construction can also cause current swells due to the use of heavy equipment and the installation of new electrical infrastructure. Conducting a surge analysis can help to identify potential sources of surges and determine the appropriate level of protection required. A surge analysis typically involves monitoring the voltage and current levels in the electrical system over a period of time to identify surge events. The data collected during the surge analysis can be used to determine the magnitude and frequency of surges entering the building and to design a protection system accordingly. The equipment grounding conductor, or EG, provides a low impedance path for fault currents to flow back to the source, allowing overcurrent protection devices to quickly trip and de-energize the circuit. It is important to ensure that the EGC is properly sized and connected throughout the building to provide adequate protection against electrical faults. The size of the EGC is determined by the size of the circuit conductors, as specified in the NEC. The EGC must be installed in the same raceway or cable as the circuit conductors to provide a low impedance path for fault currents. The number 8 solid copper ground wire from the computer network and other equipment should be properly connected to the service entrance ground bus or another approved grounding electrode. This connection provides a path for surge currents to flow to ground, protecting the equipment from damage. It is important to ensure that the connection is made using approved connectors and that the wire is properly sized to handle the expected surge currents. When installing a surge protection system, it is important to consider the location of the equipment being protected. Sensitive electronic equipment, such as computers, servers, and communication equipment, should be protected with surge suppressors at the point of use. These surge suppressors should be installed as close as possible to the equipment being protected to minimize the length of the wiring between the surge suppressor and the equipment. It is also important to consider the type of surge suppressor being used. There are two main types of surge suppressors: firstly, metal oxide varistors, or MOVs, and secondly, silicon avalanche diodes, or SADs. MOV are the most common type of surge suppressor and are used in a wide variety of applications. SAD are more expensive than MOV, but they offer better performance and longer lifespan. In addition to surge suppressors, there are other devices that can be used to protect against surges, such as isolation transformers and line conditioners. Isolation transformers provide galvanic isolation between the electrical system and the equipment being protected, preventing surges from propagating through the system. Line conditioners filter out noise and voltage fluctuations, providing a clean and stable power supply to the equipment. Regular maintenance and inspection of the lightning and surge protection system are essential to ensure that it is functioning correctly. The lightning protection system should be inspected annually by a qualified professional to ensure that all components are in good condition and that the system is properly grounded and bonded. The surge suppressors should be inspected regularly to ensure that they are still functioning properly. Surge suppressors have a limited lifespan and will eventually need to be replaced. A visual inspection of the surge suppressor can often reveal signs of damage or wear, such as discoloration or swelling. If a surge suppressor is suspected of being damaged, it should be replaced immediately. Proper documentation of the lightning and surge protection system is also important. This documentation should include a detailed description of the system, including the location of all components, the type and size of conductors used, and the grounding and bonding methods employed. The documentation should also include records of all inspections, maintenance, and repairs performed on the system. By following these best practices, it is possible to significantly reduce the risk of lightning and surge-related damage to electrical and electronic equipment. A comprehensive approach that includes proper bonding, grounding, surge protection, and regular maintenance is essential to ensure the safety and reliability of electrical systems. Remember to always consult with a qualified electrical professional when designing and installing lightning and surge protection systems. They can assess the specific needs of the building and recommend the appropriate solutions. The NEC provides comprehensive guidelines for grounding and bonding electrical systems. Adherence to these guidelines is crucial for ensuring the safety and effectiveness of the lightning and surge protection system. The NEC also specifies the requirements for surge protection devices, including their installation, location, and performance characteristics. Staying up to date with the latest edition of the NEC is essential for electrical professionals involved in lightning and surge protection. In addition to the NEC, other standards and guidelines may also be applicable depending on the specific application and location. These may include standards from organizations such as the Institute of Electrical and Electronics Engineers, or IEE, and the National Fire Protection Association, or NFPA. The effectiveness of a lightning and surge protection system depends on the quality of the installation. Proper installation practices are essential for ensuring that the system functions as intended and provides adequate protection against surges. It is important to use qualified and experienced electrical professionals for the installation of lightning and surge protection systems. Ongoing education and training are essential for electrical professionals involved in lightning and surge protection. This ensures that they stay up to date with the latest technologies, standards, and best practices. Many organizations offer training courses and certifications in lightning and surge protection. A well-designed and properly installed lightning and surge protection system is a valuable investment. It can protect sensitive electronic equipment from damage, reduce downtime, and improve the safety of occupants. The cost of a lightning and surge protection system is typically far less than the cost of repairing or replacing damaged equipment. Proper lightning and surge protection can also help to reduce insurance premiums. Many insurance companies offer discounts for buildings that are equipped with lightning and surge protection systems. In conclusion, protecting electrical systems from lightning and surge events requires a comprehensive approach that includes proper bonding, grounding, surge protection, and regular maintenance. By following best practices and consulting with qualified professionals, it is possible to significantly reduce the risk of damage and ensure the safety and reliability of electrical systems.